Hey there, class. We're here today. We're going to look at an example. This particularly is example number 3. And what we have here is a uniform beam. We're given a certain weight, and it's supported by a light string. So once again, when I see this word light string, I'm thinking kind of physics string. So again, basically think of the mass of the string as 0. It's connected to one end, making an angle of 55 degrees with the horizontal. And the other end is a pin support on a wall. We're going to try to find the tension, and we're going to try to find the net force the pin exerts on the beam. So let's take a look, kind of get a visualization of what's happening here. So this is our string here, okay? And it makes that 55-degree angle with the horizon. Of course, this right here is our beam. And we're told that it is, I believe, it was 2 meters long. So 2 meters long from there to there. And then over here, we have a pin support. So I'm just going to draw that with a little dot. But basically what a pin support means is that it is capable of supporting up and down forces, but it's also capable of supporting left and right forces. Now, a pin support does not provide any kind of additional torque around this, this location. It simply is able to provide these linear forces, the ups and downs, and the lefts and rights. All right, we're going to start off with a free body diagram. Now, this is a rigid body, so we are going to consider the entirety of the object and not just its center of mass. All right, so let's take a look at our free body diagram. First and foremost, we do have a force that acts downwards. This, of course, is the force of gravity. We know this as weight as well, and this is the 75 newtons. So that is the force of gravity. And again, this is a force on the beam because of the Earth. We also have an applied force, or I guess I should say more specifically, this is going to be tension because it is on the beam because of the, what was it because of? I think we called it a string, right? And this is actually one of the things that we're trying to find. We want to find the force of tension. We, of course, know that it makes this 55-degree angle. We'll call it theta for now, but that's making this 55-degree angle right there. All right, next we have the pin support over here on the left-hand side of the beam, and remembering that a pin support can support both up and down forces, but also left and right forces. So I know that this is going to definitely have to support somehow on the up and down. Now, I'm going to guess it's probably going to support upwards. And at this point in time, this is a guess. Now, I'm pretty sure about this because I've done these kind of problems before. But I'm going to say that the pin support here, again, this is on the beam because of the pin. And let's just call it Fy, force on beam because of the pin. It's going to be an upwards direction. And again, partially my inclination on this is if I could think about this beam and I could rotate it about the point out here on this side would fall down. So we need the pin to support upwards. Also, I notice that my tension is actually kind of pulling inwards towards the wall. And as a result, I believe that the wall is going to actually, or I guess I should say the pin more specifically, is going to have to support by pushing outwards from the wall. So this will be a force on the beam because of the pin as well. Now, I think we understand that these components, okay, would get added together and they're going to actually give us a force kind of like this. So I really should replace these two forces that I've just drawn with the component, not the component, but the resultant force. So I'm going to stop the video and I'm going to do that right now. Okay, so what I've done is I've kind of drawn this force that the pins support exerts on the beam, and it is going to be, I believe, in this upwards and kind of rightwards direction. Of course, we can draw its components. I'm going to do that on a separate picture, but that's FAX and FAY. All right, now let's take a look here. In this situation, we have what's called equilibrium, and basically several circumstances have to be satisfied to have equilibrium. First of all, the sum of the forces has to equal 0. All the forces have to add up to give us 0. And what does this mean? Well, if we think about it, this in regards to components, the sum of all the x components has to equal 0, and also the sum of all the y components has to equal 0. So this is the first condition, has to be satisfied to have equilibrium. The second condition that we have to have is that the sum of the torques about any point has to be equal to 0 as well. So this is going to be something that we are going to take advantage of as we come up with a strategy. All right, so here we are. We're going to come up with a strategy, and what I'm going to do, anytime we're using torques, we need to set a point of rotation. Now again, this point of rotation can be a physical fulcrum, but it doesn't have to be. In this case, I have chosen the point of rotation to be at the left end of our beam, and I'm going to use the clockwise direction as our positive torque direction. So, taking a look at the forces that act on our beam, we have the torque because of gravity. The torque because of gravity, we're going to have the torque because of the string, so actually let's call that torque because of tension. And then we're going to have torque because of a pin support. And these are all going to have to go together to give us basically 0. We're going to go back and we're going to take a look at what direction those are and put those in just a moment. So let me zoom out. All right, so gravity. If we set our point of rotation right here, okay, the point of rotation is at this left end, gravity is going to have a tendency to cause this thing to fall down and spin in a clockwise direction. Since we called clockwise positive, I'm going to put a positive there. The tension is going to have a tendency to pull upwards on this end, causing it to rotate in a counterclockwise direction around this point of rotation. So our torque about that place will actually be negative. And our pin support, or I guess I call it the applied force up here, this actually, believe it or not, is actually 0. It cancels out. The choice of my point of rotation being up here gives us a 0 lever arm and therefore 0 torque. So basically our torque comes down to these two torques right here, and these have to be balanced. Okay, so what I've done here is we of course know that torque is the lever arm, that's the radius or the distance from the point of rotation times our force. Keeping in mind that it also has to be a perpendicular to our lever arm. That's why this is the y component of tension. Keep in mind that our tension was at some angle here, so it's the upwards component of this tension force that we're dealing with. So that the y component would be ft sine theta, and after doing some algebra to isolate the ft, we are going to end up with this equation. All right, I'm going to do the implementation, we'll get a number, and see what we end up with. Okay, after taking our equation that we derived. All right, so after substituting those numbers in, I found out that the tension was 45.8 newtons. Now, the second part of this question required us to find the net force the pin support exerts on the beam. So that is this force right here, basically. So I can exploit the same concepts that we used before. We can take a look at the torques, and use torques to find this. Another way I could go about this, because I now know one of these forces and two of these forces, I could use the fact that their x and y components have to cancel out overall. So either way I slice it, if I wanted to do this, I have kind of two options at this point in time. Okay, so to solve this part of the problem, what I decided to do was take a look at my translational equilibrium equations. That's my sum of forces in the y direction and in the x direction. And again, these are just net force equations. And pretty much ended up solving it for the y component and the x component. I've done that actual math over here and pretty much end up with these components here. And knowing that these were only components, to put them back together again, I need to use Pythagorean theorem. And to find the angle, I actually ended up using the inverse tangent function. And lo and behold, what we notice is that there's a lot of symmetry in this problem. So this is at actually the same angle as this one is here. And that, of course, doesn't always happen, but in this particular example, because of the symmetry, what we end up with is both the tension and the applied force, this is again due to the pin, are both 45.8 newtons, and they actually both have the same angle. So we already knew this to start with, but again, 55 degrees above the horizon.